Areas in the plane. Your job is going to be to find the area between curves. You'll be given a few equations, and your job is to find the area bounded by those curves, the enclosed area. Something you'll also have to be able to do, there are certain phrases where you use unsigned area, meaning geometric area that's always positive. You've seen earlier in your calculus course that sometimes area is negative. We'll point those phrases out today when you need to be aware. The area has to be always positive. Okay. So this first example, we're just going to do this all by example. There's nothing super complicated. When you see area under the graph, that's signed area, meaning area above the curve or area above the x-axis is going to count as positive, and area below the x-axis is going to count as negative. So this is kind of the old way. Let's get some axes on here. And what does x squared minus 1 look like? And that's the point 1, 0. And this is y equals x squared minus 1. Okay, so we want the area under x squared minus 1 in between 0 and 2. So 2 is going to be right here. We want this area and this area, except because we're told area under the graph, this area here is going to count as positive since each rectangle would have a positive height and a positive width. Each rectangle in this region would have a positive width but a negative height. So this is a pretty easy integral to write. If we think about any one of these rectangles, its height, maybe we should write it height, is going to be given by x squared minus 1. And each width is going to be given by a very, very tiny change in x. We call that dx. So we want to add up infinitely many of those, starting at x equals 0 and finishing at x equals 2. So maybe we can clean that up. 0 to 2, x squared minus 1 dx. And let's go ahead and evaluate that. The antiderivative of x squared is 1/3 x cubed. The antiderivative of 1 with respect to x is x. And we're going to evaluate from x equals 0 to x equals 2. 1/3 of 2 cubed minus 2 minus 1/3 of 0 cubed minus 0. And so what we end up with, let's just leave this as 8/3 minus 2. Okay, so that's pretty straightforward. If you can do that, you can do pretty much everything in this lesson. Notice we're given a slightly different phrase. We're given area bounded by. When you see area bounded by, that's talking about geometric area. We're going to make all the areas positive. Although in this case, I don't think that's much to worry about. So x squared and 3x, our first job is going to be to visualize. So what does x squared look like? Well, that's what x squared looks like. And 3x, ooh, that's one of these intersection points. So I think it's pretty obvious, but maybe not, that we're looking for the area of this, let's call it banana-shaped region. Are there any other places that might be bounded by these two curves? No. If we think about this, kind of extending on forever, this region is unbounded on the left side. this over here would be unbounded down to the right. Up here, there's no top boundary. Yeah, the only place that could possibly be bounded by those curves, meaning totally enclosed, would be this region we've already identified. So after we identify the region we're talking about, we draw what's called a representative rectangle. Since integrals are really adding up the areas of lots of rectangles. Okay. And that's just going to be height times width. Turns out the width is the easy part. The width is a very, very tiny change in x. We're going to call that dx. The height is slightly more complicated. Well, how tall is the height? The height is definitely less than 3x, so let's start with 3x. And then we're going to subtract x squared. Let's move that over. I thought that was going to be bigger. Okay. Why is it 3x minus x squared? Well, let's think about this. Let's just make up some numbers. Let's say this had a y value of 4, and this y value was 3. That's pretty obvious that the distance between these two spots is 1 unit. Okay. How do we get that? We went 4 minus 3, top minus bottom. Okay. So the area of each of these rectangles, no matter where they are, the height is going to be 3x minus x squared, and the width is going to be dx. If we're going to add up a bunch of these, we're going to need an integral, and we kind of went out of order. Usually the best thing to do is to find these intersection points. Now we all know, I think we do, 0, 0 up here, and then, well, you can probably figure out in your head this intersection point is 3, 9. Okay. If you couldn't figure that out logically, or you had something complicated, all you would have to do was set x squared equal to 3x, solve, and don't divide by x, move everything to one side so you lose something. And you'd find your two intersection points. So we're going to integrate from x equals 0 to x equals 3. All right, let's get rid of all this. And I'll go ahead and finish integrating. Because we do want the area, that area better be positive if we've done everything correctly. Okay. Woo! The antiderivative of, what are we doing here? 3x is 3x squared divided by 2. The antiderivative of x squared is x cubed divided by 3. And we're going to evaluate that from x equals 0 to x equals 3. 3 times 3 squared over 2 minus 3 cubed over 3 minus 3 times 0 squared over 2. Oh, no parentheses yet. Minus 0 cubed over 3. Okay, so what do we get? So that's 27 halves minus 9. And yay, AP Calculus, we don't have to simplify. But we better make sure this is a positive number, so maybe we should simplify. So let's see, 27 over 2 minus, that'd be 18 over 2. We definitely get a positive number. Whenever you see area bounded by graphs, we're talking about an always positive area. So this is an important idea. It's not, I don't know, it's super simple to remember, but why is this true? The height of each rectangle is always top minus bottom. Well, you saw in the last example, when you have two functions that are both above the x-axis, height of that rectangle is the top minus the bottom. Okay, so hopefully that makes sense. Hey, we're good to go. Let's explain the other two cases. What if we had one function above the x-axis and one function below the x-axis? Let's call this f of x. And let's call this g of x down here. So if we draw a representative rectangle, the width of that rectangle is still going to be dx. No problem there. But what about the height? In this case, we want an always positive height. So what I said is, hey, it's always top minus bottom, or in this case, f minus g. Well, let's make up some numbers. Let's say this is something reasonable like 2, and this is something reasonable like -3. Well, if you're in calculus, you know that height distance is definitely 5. What did you do? Well, hopefully you did 2, which is the value of f of x. Let's call this place c. That'll be better. So f of c minus g of c. Top minus bottom gives you that height of 5. Okay. There is another option. So we had both curves above the x-axis, one curve above, one curve below. What if you had two curves below the x-axis? So let's leave g where it is. And let's get rid of g. I need to move my axis a little higher. Oh, we'll get rid of everything. Okay. There's g of x. And let's put f of x underneath. Draw a representative rectangle. And what would the height of that rectangle be if we want this always positive version? So let's say this is happening at C. Let's make up some numbers. Let's say g of c is -1 and f of c is -5. How tall is this rectangle? Well, I think we can all agree that's a 4. How did you get 4? Well, you did -1, which is g of c, minus f of c, which is -5. You did 1 minus -5, or 4. Now, you might be a little confused why, those of you who are noticing details, I have top in quotation marks. How come? Well, because top and bottom don't always mean top and bottom. If you go back to the objectives, you're going to have curves in terms of x and y. Let me say that another way. So what if you had this f of y and this g of y? Well, you can't really do actual top, meaning vertically higher to vertically lower. That doesn't work. So in this case, we want top kind of means larger, and bottom means smaller. And so if we had drawn a representative rectangle, that rectangle would go horizontal. Which means, what's this height? This height is a very small change in y. That's going to be dy. And what's the width going to be? That width is going to be the larger. Is the larger f or is the larger g? Well, to the right on a number line is larger numbers. So this length would be the larger one, f of y, because it's on the right. minus g of y, the smaller, which is on the left. We'll do an example of this right now. So first, we have to sketch 4x equals y squared and y equals 2x minus 4. Let's start with 2x minus 4. I think most of us are going to agree. We're more comfortable there. Okay. Since we're sketching, really all we care about is approximate places. So if you're thinking that slope isn't 2, well, you're right, it doesn't look like 2, but that really doesn't matter. So let's try to graph 4x equals y squared. Excuse me. 4x equals y squared definitely contains the point 0, 0. And then what else? It contains the point 4, 4, which is, I don't know, somewhere up here. And then it also contains the point 4, negative 4. So we're looking at, not a parabola. Well, it's supposed to be a parabola. I'm just not great at drawing, apparently. Okay, so something like that. We're looking, oh no. I hit my eraser button. We're looking for that region right there. Maybe we should do it. So let's draw a representative rectangle. Well, again, I can't draw a vertical rectangle. That would mean the height would be, I guess, 4x equals y squared minus itself. That isn't going to work. Let's get rid of that rectangle. I guess we're getting rid of all of it. We're going to draw our rectangle horizontally. So all we have to do is height times width. Although in this case, I think we want our height second, so things look normal. So we'll do width first, multiplied by height. You'll see what I mean in a second. What's the height of each of these rectangles? They're all going to be a very small change in y. We like to have that dy rules. And now what's the width going to be? Well, it's going to be something minus something. And, well, it's going to be the line minus the parabola. Okay, the line is always to the right, so it's kind of on top. It has a larger value than the parabola, which is on left. But we have a problem, and that is this dy means everything needs to be in terms of y. So we're going to have to do some algebra to rearrange. Probably should have done that first. Oh well. Let's get rid of all this so I have some room to do algebra. You can, of course, rewind the video if you need to see it. Okay, so let's see. 4x equals y squared. That's the line. X equals y squared over 2. Okay, and then our parabola. Oh no, get it together. Okay, and then let's get the line. Y equals 2x minus 4. Y plus 4 equals 2x. X equals 1/2 y plus 2. Okay, now many of us might be realizing we need to add up all those rectangles, and we need to go from intersection point to intersection point. Well, I never found those. so let's go back real quick. We had something about like this. We need to find those two intersection points. So let's set, what do I want to do? Well, I don't know. How about I set, let's see, we had 4x equals y squared, which gave us y squared over 4, which you may have realized I made a huge mistake on. Okay. And let's put that in this x. So we're going to have y is equal to 2 y squared over 4 minus 4. Y is equal to 1/2 y squared minus 4. And let's multiply everything by 2. 2y equals y squared minus 8. Keep going. Y squared minus 2y minus 8 equals 0. And can we factor? We sure can. That's going to be y minus 4. Y plus 2 equal to 0. Doesn't look like 2 at all. And so y is equal to 4. Y is equal to negative 2. So this is sum x, negative 2. And this is sum x, positive 4. So turns out we don't need those x values because we just needed to know these bounds of integration, because we're going to start stacking rectangles here at negative 2 and keep filling this thing up all the way until y equals positive 4. Hopefully you can integrate this whole thing. It's not terribly hard. I'm not going to finish, but let's make sure we can do this. So let's see, what's the antiderivative of 1/2 y? That's going to be y squared. Let's go back. Let's see, y squared times 1/4 plus 2y minus, that's got to be a y cubed over 12. And we're going to evaluate from y equals negative 2 to y equals 4. I'm assuming you can finish from there. Okay. Let's try to go in order of everything important here. So area bounded by x cubed and 4x. Since we see area of the region bounded by, we're talking about always positive area. That's going to be super important here. Let's see, x cubed looks something like that. And 4x also goes through 0, 0, so I have one intersection point. Okay, so that's 0, 0. Let's get all the intersection points ahead of time. So we're going to say, what? X cubed equals 4x Okay, so these three intersection points, negative 2, negative 8, 0, 0, and 2, 8. Okay. So what are we looking for? We are looking for, can you identify the region bounded? It's kind of a trick question. There are two regions bounded by x cubed and 4x. We need to find the sum of those two areas. So what we do, let's draw a representative rectangle. So for this rectangle, it's line on top and the cubic on the bottom. for this region, it's cubic on top and line on the bottom. So let's set those up. So we're just thinking width times height. And so we'll do the red one first. The height, oh, we want to have height first, don't we? Well, we'll just switch that around. The height is going to be 4x minus x cubed. And the width, that's pretty easy. That's a super tiny change in x. That's a dx. Now what about the blue one? That's height times width as well. The height there is going to be the cubic, x cubed, minus the line, 4x, and the width of that is also dx. So we're going to add those two things together. Where are we integrating the blue one? From x equals -2 to x equals 0. Where are we integrating the red one? From x equals 0 to x equals 2. Now, some of you super intelligent people in the crowd may have noticed that y equals x cubed and y equals 4x are both odd functions, which means these two areas are exactly the same. Well, they have the same numerical value of the two areas. So what we could do instead is just say, well, I'd like to have this bound from 0 to 2. That'd be easy, of 4x minus x cubed dx. But I know the area is doubled, so I'll just double everything. There we go. There's one more way to go. If you're doing this with a calculator, you could also do, no, you're not going to have the 2 out front. You're going to do the definite integral from -2 to 2, and we want everything positive. This is only with a calculator. And it turns out it doesn't matter what order. If we're using a calculator to do absolute value, 4x minus x cubed is always going to be positive inside that absolute value. But we're not going to be using a calculator for the next couple of days while we're trying to get this idea.